All right, so now let's look at some examples. Here's example 1. At the state fair, you could play Fish for Cash, a game of chance that costs $1 to play. Same thing. You blindly fish out a card that has the dollar amount that you have won from a giant fishbowl. They're having a special where when you draw a ticket, they will triple the value printed on it. What is the expected value and variance of this promotional game? All right. So if you download the examples and you go to example 1, I've put the original game on here with all the winnings, including 0, and the probability of those winnings. So here we want to sum these up and make sure it adds up to 1 so that we know that our probability distribution is complete. All right. And so now let's talk about just plain old regular expected value of this old original game. So I just multiplied x by p of x. So it's the contribution of each value of this random variable, right? And then the expected value in total is just that sum, right? And this we've done before. The reason I want to do this is I briefly want to just show you how to calculate the variance. So here I have standard deviation. So whatever we have here, we're going to have to square root it. And so let me just put a note to myself here. I'm going to need to square root this, right? But let's think about how to calculate variance here. So this is the expected value, the mean, right? But what's the spread around that mean? Well, we're going to have to know what x, so x is over here, winnings, right, minus the mean, the expected value, squared is. So the squared deviations away from our expected value. There we go. And to all of this, I'm going to multiply. So I'm going to put all this in parentheses. And then I'm going to multiply the probability of that particular x. Because this is sort of saying, okay, here's the squared deviation, and the probability tells us how much should this squared deviation count. Should it count only a little? Should it count a lot, right? And then I will just copy and paste that all the way down. And what we do here is we need to square root the sum of all of these. Square root the sum of all of these guys. So that's the spread around this mean. Now notice that, let's think about this. If our expected value is 60 cents, and our spread is around $4, right, because it's standard deviation, then that means if we go on the negative side, that's going to be in the negative numbers. Now, you can't necessarily lose money on this game. You're not going to pull out a card that says, give me $3, right? So that doesn't really make sense. But what it's saying is that this number is large because you're being pulled by these big values, like that 900 number, right? So this is saying it's probably skewed on the right side towards the larger numbers. So there's a long tail there. Okay, but let's get on to our problem. Now, this is the problem where we're talking about the new probability of winnings. So here's the old probability of winnings. And actually, the probabilities don't change. Your chance of drawing a 0 card remains the same. But the value of those winnings have changed. So it's now 0 times 3, which is still 0, unfortunately. But all these other ones, you can now win up to $2,700 in this game. Is this game a good deal? Well, let's see. Let's find the expected value. So here, we're no longer using the old x, but we're using sort of the new x. And this new x is really 3x, right? So our d is 3. So the new winnings times the probability of those new winnings. And I'm just going to copy and paste that all the way down. And then sum that up. Oops, sum. And I get $1.80. This new game is a better deal because over time, if you spend, for every dollar you spend, you'll get $1.80 back. So not on any particular draw of a card will you get $1.80, but if you played this game 100 times and you spend $100, on average, you'll get an extra $80. Great. Well, let's also see if we could find that using our like shortcuts, right? So before it was mu sub x, right? And it said, okay, if you want to transform all your values by multiplying it by d, then all you do is you multiply your old expected value by d, right? And is that the case? Yes, it is. So I could do this old expected value times 3 and get that same value. So ta-da! So you could use that shortcut. Now let's calculate standard deviation. Well, we know that in order to calculate we know to calculate variance, it's d squared times variance. But here we have standard deviation, so it's just d times standard deviation. Let's see if that works. So d times the standard deviation, we should get $12.12. So the variance has gotten bigger, right? Because the spread has gotten bigger, because now you can win all the way up to $2,700 or zero, right? So we've really increased that spread, right? But we could also check and see if this works sort of conceptually, right? So here we're going to want to take the value of the new winnings minus this expected value squared. Let's see where I am. Oh. All right, but we want to lock this guy down because our expected value won't change. And we want to take that squared deviation and multiply it by the probability. So we could just copy and paste this all the way down. And here, remember, we need to find a standard deviation rather than variance, so we need to square root the sum of all of these. So what you can think of these multiplying by p as it's already sort of done the division for you, you know. And what do you know? We get about 1212. So if we had looked at this in a larger, with more decimal points, we would see the exact same number. So voila, it works. Our shortcuts work, and also the regular old formula for variance also works. Great. Example 2. Suppose you buy 3 tickets from Fish for Cash. What is the expected value of your total winnings? Total winnings. What about the standard deviation? And which standard deviation is higher, playing the game 3 times or tripling the value of one play? Why? Okay, so now we know that this is the situation where we get 3 independent events and then we add them together, right? And so that's like estimating, okay, the first x, we estimate that to be the expected value. The second x, we estimate that to be the expected value. The third x, we expect that to be the expected value, right? So that's going to be the expected value, the mu of x1 plus x2 plus x3. I'm just going to shorten that to be mu of sum, right, whatever the sum is going to be n times the old expected value, right? And so previously our expected value was 60 cents, right? and our n is 3. So this is $1.80. And that's the same as before, right? And we've established that already. These two situations have very similar expected values. What about standard deviation? Well, the standard deviation of sum, that's going to be my new x, right, is the square root of n times whatever the standard deviation was before. So standard deviation. All right, so that's going to be the square root of 3 times, and let's look up what our standard deviation was before, $4.04. 4.04, right? And let me just use a line of my Excel here just to calculate that. So square root of 3, you could feel free to use a calculator, times 4.04. And that's going to be 6.98. So 6.98, right? And we saw that in the previous so the tripling the value one, the standard deviation of 3x, that was $12.12, right? So which standard deviation is higher, this one or this one? Well, it's certainly this one. Why is that? Well, because we've really expanded the values, right, of the x's, right? Now you can win up to 2,700 in one play, right? And the chance of that hasn't changed. Whereas here, if you pick out 3 cards, there's a very, 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 very slim chance that you're going to get 3,900 cards, right? And so that probability way out there, it's not likely in this case. But here, it's more likely than in this situation. So it makes sense that here we've really stretched out the values. Here we haven't stretched out the values as much. But notably, we have increased the standard deviation from the original game. Okay, example 3. This year there are 2 booths owned by Amos and Bobby with similar games to the Fish for Cash game. Amos's booth has an expected value of 0.50 with a standard deviation of 0.25. Bobby's booth has an expected value of 0.75 and a standard deviation of 0.32. Not counting the cost of the ticket, which I presume is $1, what are your total expected winnings and what is the standard deviation? So I'm going to say, what are your total expected winnings if you play each game once, so that you have to add together those two. Let me make sure I have my Excel handy for later. All right. So let's think about this first. So what we really want is we have Amos's game and Bobby's game, and we're going to take our winnings from both of them and add them together. So we have A plus B, right? And we want to know what is the expected value of A plus B. So we know that mu of A plus B is equal to the mu of A plus the mu of B, right? And we have mu of A and B. So expected value of Amos's booth is 50%, right? And the expected value of Bobby's booth is 0.75. So we add that together. The new mu is $1.25. Hey, good news, right? So that's good news only if you discount the fact that you spent $2 to win $1.25. So not good for you, but good for Amos and Bobby, right? Okay, so what is the standard deviation of these? Well, we actually don't know directly the standard deviation formula. We could actually derive it from what we do know. We do know variance, right? So we know the variance if we add together the variance of A, if we want the variance of A and B added together, then all we do is add the variance of A to the variance of B. Variance of B. Oh, I keep writing A instead of sigma. It's very similar. Sort of turned. All right. So this is our formula for variance, but it's asking for standard deviation, right? So we might just square root both sides. And we know these values already. Oh, we don't know standard deviation. We don't know variance. We only know standard deviation, but we know how to get variance, right? So you'll have to take the square root of Amos's standard deviation. I'll show it in blue, right? So in order to find variance, I have to square that, right? I don't need these parentheses anymore. I have to square that first and add it to Bobby's standard deviation squared in order to get variance. And the reason we have to do this first is that the square root of this sum is not going to be 0.25 plus 0.32. There's order of operations. You have to do the squares first before adding them together. And if you don't, that's going to change the value, right? So let's see what we get. Well, I'm just going to use one of these rows to help me out here, just so I could calculate some things. So here I'm going to write square root of 0.25 squared plus 0.32 squared. And the nice thing is Excel, sometimes better than us, knows order of operations. Excel knows that it needs to do the powers, the exponents first, and then add them together. And then all of that, square root of all of that, square root of that sum. And we get 0.406. 0.406. So that is our new standard deviation. It is larger than either of them alone. And that makes sense because we're increasing variance because we're adding things together.